Okay, okay. So, see, and yes, Fatima, how are you? Fatima Munir? I think
I'm good.
I've joined a long time back, no? All right,
Yeah.
Fatima. So, see, I think you should continue in this batch only now. Here we will start with a revision of all the lessons from the next class. Right now, we are currently completing the last lesson of your syllabus, that is semiconductor. So yesterday only we started some portions of it, initial portions of it, we have covered it. Rest of the part we'll complete it today. So wherever you're not able to understand anything, both of you and for other students as well who had attended the class yesterday, you all can ask me regarding the things that have been missed by all of you, not just Aaron or Fatima. We'll be covering from the starting. Fatima has attended many of the classes as well. Some of the lessons of first book was missed, and I think the second book got missed. So that we'll start with a revision class next weekend. So from the first chapter we'll start. So everyone will can attend those classes. Right now, let's continue with semiconductors. See, we started with the fact that whatever properties conductors have, whatever properties insulators have, like insulators have high resistivity, conductors have low resistivity, while insulators have low conductivity, conductors have high conductivity. But regarding semiconductors, when we talk particularly about these semiconductors, they have the properties in between. The properties of semiconductors lie between conductors and insulators. So one important theory we had, which was known as energy band gap theory, in which you have various energy levels, right? You have various energy levels from which electron jumps from one level to another level. The detailed mechanism of how electron jumps, frequency emits, that we have done in the electromagnetic, the spectral series of hydrogen in atoms. So see, electrons are currently bounded in valence bond, in the valence band, and from here it, when it receives a necessary amount of thermal energy, it activates and moves through the conduction band, and from the conduction band electrons are available for conduction. Now three basic differences we had seen between the three insulators, conductors and semiconductors. In conductors, you will notice that conduction band is partly filled with electrons and valence band is completely filled with electrons. Valence band completely filled, but conduction band will also be partly filled with electrons. It can have energy band gap. See, what is energy band? Energy band is the difference, this gap that arises between the conduction and valence band. Or it can overlap with each other like this. So it can be completely filled or partly filled conduction band. Valence band has to be completely filled with energy gap or without energy gap with overlapping. This is how you identify a conductor. Regarding insulators, insulators and semiconductors both will have their conduction bands completely empty. Conduction bands will be completely empty. But how will you differentiate between insulators and semiconductors? In insulators, you will notice that energy gap is large. That's why we call it insulator. Electrons find it very difficult to cross this energy gap and reach the conduction band for conduction. That's why we say insulators are poor conductors of electricity, because they're not able to conduct or pass electrons through them just because of this energy gap. So if energy gap is very large, more than 3 electron volt, we'll say it is an insulator. Just contrary to this, again, conduction band empty, valence band fully filled, but energy gapping will be very less. Energy gap will be less than 3 electron volts. If you see such a case like the energy gap of silicon, energy gap of germanium, then we'll categorize it as semiconductors. So this is what we had covered in the last class. Now see, now this is the differentiation part is over. We have classified all these. Now we'll just be focusing on semiconductors, nothing else. Now we'll just focus on semiconductors. See, this is the classification of semiconductors class. Firstly, you have intrinsic semiconductors, which are also known as the pure semiconductors, means no other element has been added. This we'll discuss in detail, as well as we have to discuss this also, extrinsic semiconductors. These extrinsic semiconductors are very important from your examination point of view. This is very important. This is also we are going to do, but extrinsic semiconductors are supremely important. Now, extrinsic conductors, depending upon the type of impurity that has been added, they are also classified as p-type and n-type. So type of semiconductors, intrinsic semiconductors and extrinsic semiconductors. Extrinsic semiconductors are of two types, p-type and n-type. Now we'll see, firstly we'll complete this extrinsic semiconductors part, then we'll come to extrinsic semiconductors. But see, before we go into the details of this extrinsic, intrinsic, no class, firstly let us see what is the actual mechanism that occurs. That basic mechanism will be same for extrinsic or intrinsic. See, suppose you have a crystal. Let's say silicon crystal exists. Fine. So if silicon crystal exists, so silicon will be having, let's say, 4 electrons it is having in its outermost shell. It is having 4 electrons. And we take another silicon. So this silicon, they will share a bond. Likewise, all the silicon atoms will be sharing a bond with the rest of the silicon atoms. That will result in formation of a complete crystal lattice. Now see, class, just these two terms, please be aware of this because this will be used throughout. Electrons and holes. See, these electrons are negative entities. You all are aware of electrons, the negative charge that an electron holds. About electrons, we have studied in electrostats. See class, if somehow this electron-electron bond is broken like this, from here you can say this bond is broken, something, the electron bond is broken, and one of the electron moves away like this. The electron moves away. So class, this was electron, the negative part, and when there is deficiency of electron, the quantity that is created, the entity that is created, positive charge will be created because of deficiency of negative charges. So that positive part that is created, it is known as hole. So why am I emphasizing on this? Because this, all of you know that when electrons are not present, that deficiency of electron creates positivity. All of you know this. Reason why am I telling you this? Because in your electronic physics, that is in your semiconductors, we treat hole as separate entity, which is hypothetical because when an electron moves, its vacancy creates a hole, right? But you'll notice we'll be considering hole as another entity. That is just for making our theory part easier, right? Like holes are moving, electrons are moving, holes are getting more in quantity, holes number is increasing, holes number is decreasing. Like this, the way we talk about electrons, similarly we'll be talking about holes as well. That's why I'm just telling you that actually holes are what? Holes are just efficiency of electron. But that deficiency, because this is such an instantaneous process, all the movement of electrons, that we consider holes as separate entity. Right, class? So let's start with intrinsic semiconductors, or do one thing. Note down this part, the type of semiconductors and this basic note. Then we'll start with it. Intrinsic first we'll cover, this intrinsic part. You'll understand intrinsic, extrinsic we'll do that. Done.
Yes, ma'am.
All right, now let's start with intrinsic semiconductors. See, intrinsic semiconductors, you first understand the meaning of intrinsic semiconductors. Then you will be able to differentiate it from extrinsic. See class, right now what I have drawn, all the silicon atoms are present. You are not able to identify any other element like boron, helium, aluminium, gallium, no other element, germanium, no other element you are able to see. It means in the entire crystal lattice of silicon, you will be just able to identify silicon everywhere. All the silicon bonds will be formed, all the covalent bonds will be formed between two silicon atoms. No other element is formed. So such crystals which are having pure atoms, no other atom has been added for any purpose. That pure atom is known as intrinsic, which means pure. So intrinsic semiconductors means pure semiconductors. Fine. The meaning of intrinsic semiconductors is pure. Now see, this bond that has been drawn, no, this is actually the same bond. This bond that has been drawn is actually the same bond. Let me tell you. We draw one silicon with this, like this, we draw the bond, the above bond which I had shown you. What I have drawn is, this is one electron of one silicon, this is electron of another silicon, just like this. Why have I drawn it like this? See, reason for drawing it like this is just so that you are aware of the bonding of one electron and then the bonding of another electron. So same thing, this way only. This means same, this single bond. Now see class, what mechanism actually occurs here? See, all the electrons are bonded, no other element is present. So what happens if you increase the temperature, this is at normal room temperature, all the crystal lattices are fine, all the silicon atoms present within the crystal is also perfect. Now, as we increase the temperature, thermal energy gets increased, thermal energy of the conductor gets increased. So this results, this high energy breaks this bond, this electron-electron bond that is present. It breaks this up. So if electrons become free for conduction to occur or electricity to move, the electron will move away. What did we study just now? The vacancy, the deficiency of electron will create positive hole. It means over here, a positive hole will be created while the electron will move away for conduction to occur. So this electron, this free electron will conduct electricity while there will be a hole developed. Now see, if two such electrons move away, two holes will be developed. If four electrons move away, four holes will be developed. If I say n number of electrons move away, so n number of holes will be developed. This shows what? Whatever is the amount of holes, that is exactly equal to amount of electrons present. Because as the electrons are moving, holes are getting created. If a single electron moves, a single hole will be created. This is known as intrinsic semiconductor, and this is how the working occurs. Temperature increases, thermal energy increases, electrons bond breaks, the covalent bond breaks, and the free electron becomes available for electricity. And this free electron ultimately conducts electricity. It moves, and it conducts electricity. This is the basic mechanism. And number of electrons is equal to number of holes. Basic mechanism is by the thermal generated mechanism. Now see class, there are a few limitations of it. This we have already discussed, the energy gap for silicon, energy gap for germanium. Class, I have told you, please remember at least the energy gaps values for silicon and germanium. These two values can be asked in your board exam, and if it is asked, then you'll not be able to help yourself because the values are one single definite that is given in your textbook. So since this value is mentioned in the textbook, please do not leave this, just these two values, remember it as the energy gap. And whenever you're answering and giving your theoretical answers, the large subjective answers which you give, and if such a question comes, try to mention this, try to show this value, 1.1 electron volt for silicon and 0.72 electron volt for germanium, because this will prove also that silicon and germanium are semiconductors, as well as a definite value of energy gap will be given. Now see, intrinsic semiconductors have certain limitations. Firstly, the number of electrons and number of holes are very small because there is not enough temperature available for the electron-electron bond to break. Unless and until this bond breaks between them, one electron, this bond breaks in between them, then only this electron will be available for conduction. And very few electrons are able to actually reside their place. And when they leave their place, then only holes will be created. So there's this ratio of holes entering and electrons leaving. This is actually very less. It means in 1 millimeter cube, in 1 meter cube part, you will be able to find just 10 to the power 6 electrons, which is actually very less. If you look at microscopically, this is very less. So 10 to the power 6 per meter cube. This means in 1 meter cube, you have 10 to the power 6. Fine, this is one of the limitations. Second limitations that is present is the energy gap is quite large. So whenever the energy gap will be large, the energy gap for the silicon, no, this you can see it is very large. For silicon and germanium also you can look. So when energy gap is large for intrinsic semiconductors, conduction process again becomes slow. Right, this again becomes slow. So for industrial applications, for daily life applications, this is not very helpful. We need something that is fast, that gives you more advantages, that can be modified according to your needs. So because of all these limitations, it led to the development of extrinsic semiconductors. Now intrinsic was pure, extrinsic are not pure. So let us start. Okay, before we start with it, note down intrinsic semiconductors. Any doubts you have, ask me, get it clarified. Then we'll start with extrinsic. Intrinsic semiconductors are not very important from your examination perspective. Extrinsic semiconductors are very much.
Ma'am, could you scroll up for a second? Yes, ma'am, done.
I hope all of you have written till here. Let's start with extrinsic semiconductors, and please pay attention when we are doing extrinsic, because this is the basic for your PN junction. As in the last class also I have told you, semiconductors is not now lengthy. Many topics have been deleted. Two topics are there. This is just N-type, P-type, this part that we are going to start with, and the PN junction part. Nothing else is going to come in your exam even. So just pay attention to this part. Yes, students who are preparing for their entrances, in your entrance, the other parts will also come. Now, see extrinsic semiconductors. Now see, I had this silicon atom, right? This silicon atoms. Now, if I intentionally, voluntarily, if I put, let's say, arsenic in it, so it will be silicon everywhere with arsenic, very few arsenic atoms present in between. So these arsenic atoms, which are getting induced voluntarily into the pure crystal, making the crystal impure, these atoms are known as dopants. This entire process of adding these atoms, the entire process of adding the dopants in the pure crystals is known as doping. And the semiconductors are themselves known as extrinsic semiconductors. I'm repeating. See, certain atoms that are added in the pure crystal, these atoms make the pure crystal impure because these are not of the same type of atom. A different type of atom is taken. So the process of addition of these atoms, this is known as doping. The atoms which are voluntarily added are known as dopants. And this entire semiconductor that is formed is now called extrinsic. It is no more pure. This is no more intrinsic. Now this is extrinsic semiconductor. Now, depending on the type of dopant, the atom which you are inducing in the pure crystal. The silicon crystal you had, now you have added arsenic. So this type, what has been added, whether arsenic, whether phosphorus, what has been added, that determines your p-type and n-type. So one type are pentavalent dopants, other type are trivalent dopants. Very easy to understand. Dopants having 5 electrons in their valence shell. All the phosphorus family, phosphorus, arsenic, bismuth and all, that part will come, right? This part will come. And trivalent dopants having 3 electrons in their valence shell. The boron family. Boron, indium, aluminium, gallium, thallium. This entire family will come. Because how do you write it? Aluminium, you write it in this way only, no? Al3 plus. So having 3 electrons in the valence shell. Similarly, phosphorus, you write it this way, having 5 electrons in the valence shell, right? So these are known as dopants, and this process is known as doping. So aluminium can be a dopant, phosphorus can be a dopant, gallium, and yes, gallium and bismuth and arsenic, any can be a dopant, right? So these are extrinsic. Now let's start with the first one. See, if pentavalent dopants are added, if these pentavalent dopants are added, then the type of semiconductor we get is the n-type semiconductors. The type of semiconductors that we get, these are n-type semiconductors, right? And if contrary to this, trivalent atoms are added. Contrary to this, if trivalent atoms are added, then we say these are p-type. So yes, n-type. Pentavalent dopants added, n-type. Trivalent dopant added, p-type. Do not learn it this way, pentavalent p and p-type. No, class. Otherwise, it will reverse your theory and the whole entire characteristic of it. N-type means pentavalent dopants have been added. So see, silicon or germanium, all these family. Let's say silicon crystal lattice is there. 4 electrons are present everywhere. So it also needs neighboring 4 electrons to complete its octet, because 4 electrons are already present. Silicon needs 4 more electrons to complete its octet. So 4 electrons should be provided by other silicons or any other element that has 4 electrons available. But when we add pentavalent dopant, pentavalent has 5 electrons in its valence shell. So 4 electrons will tie a bond with the silicon. But what about the 1 electron that will be left? 1 electron will be left, right? So this is a very weakly bounded electron which is available for conduction to occur, because now there is no more need of it. So this is just one case. Now see how many phosphorus atoms are present. Few dopants have been added. Definitely number of silicons will be more than number of phosphorus, but number of phosphorus will be something. It will make the number of electrons more at least. So here the difference that you will see from intrinsic conductors are, the first point is that number of electrons is greater than number of holes, because these are donor atoms. Phosphorus has donated atoms. These dopants, the pentavalent dopants, these are known as donor atoms because they have extra electrons. They donate electrons. One is this process. See, two processes are there, class, how electrons are getting generated. One is directly phosphorus is giving you this electron. Take this electron from me. Take this extra electron from me. I have this electron extra, take it from me. So that is just by the donor atom. One way you have number of electrons. And second way is the way that we saw in intrinsic, thermally generated mechanism. If you give certain energy, thermal energy will be high, then free electrons will become available from the bond. So more number of electrons are now generated. One mechanism remains the same, that thermal energy mechanism, but one more additional mechanism which contributes to electron formation and giving of electron number is this weakly bounded electrons that are additional in the pentavalent dopants. This energy value, no need to remember this. This is just the data that I'm telling you. Approximately 0.045 electron volt is needed. So I'm repeating this. Silicon-silicon bond was everywhere. In between, a third party, that is phosphorus, entered. Now phosphorus had extra electrons. 4 electrons contributed to the bonds with the silicon, so 4 covalent bonds were easily formed. Thermal energy, if you give energy, thermal energy will increase, covalent bond will break, free electron will be available, so electron number will become high. First point. Secondly, these additional electrons which are present, not for just this phosphorus, all the phosphorus that are added, that will also contribute in increasing the electron number more. So in totality, you will have number of electrons more than number of holes, and these are just because of the pentavalent dopants, which are known as donor atoms. And impurities which are added, the unit, it could be in mole also, it could have been in molar units also. So the unit that is decided for impurity is ppm, because these are very small, so added in ppm. So yes, this I was telling you, electrons are generated by two mechanisms. One is through donor atom, directly donor atom is giving you, and second is thermally generated, means hole is there, hole that is giving you. And number density of electrons is very much greater than number density of holes. In intrinsic semiconductors, we had the number of electrons and number of holes exactly equal. See class, the energy gap that you draw, energy gap, same energy gap that we saw in the last class yesterday. So the energy gap for these elements, the n-type, this lies somewhere near the conduction band over here, somewhere here near the conduction band. So the value is around 0.01 electron volt for germanium and 0.045 electron volt for silicon. This I have told you 0.045. This is not very important. These are actually the ionization energies values for silicon and germanium. So this is not so much important, but those two values which I told you, 1.1 and 0.72, the energy gap, that class please, ma'am. That I think if it is asked, then you'll not be able to recall or perform any guesswork. So this is how the energy band is drawn. First, tell me class, is this n-type clear? If n-type is clear, then only I'll move ahead. This is clear by all of you?
Yes, ma'am.
Yes, ma'am.
Others apart from Anushka and Fatima, clear or not?
Yeah, ma'am.
Okay. So p-type is now very easy. If you have understood n-type, see, p-type is much more simpler than this. What will happen? Just the story in reverse. Here you have silicon atoms we have taken, but we have taken trivalent dopants. It means you have silicon atoms which are having 4 electrons, right? The silicon atom is having 4 electrons. Now see what will happen. Silicon is present with its 4 electron. So to complete its octet, it needs minimum 4 electrons. Phosphorus had extra electron. It gave 4, it gave extra also. But what about here, the trivalent dopant? Let's say aluminium has been added. It could be any element class. For example purpose, I'm taking aluminium or phosphorus, fine. So aluminium will be having 3 electrons. So 1 electron of aluminium, second electron of aluminium, third electron. Finished. This will bond with it. One will be left empty. Right, all the bonds will not be able to form. Right, one portion of silicon will still remain empty. Look here in this crystal. One bond will still be empty. Let's say this is 1 electron of it. This is second electron of aluminium. This is third electron of aluminium. Fourth one is empty. Let's say here the electron is not present. So to maintain this bond, till now no hole is there class, because electrons have not moved. If I say at this particular box, no electron is present, so it should be a hole because electron is different. No, until and unless an electron moves from its place, then the place gets created by a hole. So here we won't say a hole is there, because, or here I won't say a hole is there. 3 electrons are present, that's it. If the electron moves, then only a hole will be created. Right now nothing is there. So what happens? The adjacent silicon, this breaks the bond and this electron moves and reaches here. Now aluminium has 4 electrons. It will fulfill all the silicons that are present beside it, and at least aluminium will be full. Now C class, the movement of electron or the removal of the electron. Now this creates a hole. So do you see number of holes generated will be more because so many aluminiums are present, and to fulfill all the aluminium atoms that are present, holes will keep on getting created. So one method is this, and second, this is how the electrons are generated. Secondly, how the electrons are generated is by thermal mechanism. That is same for intrinsic. Again, they are added in ppm, right? They are again added in ppm. And see, now the energy gap will lie near the valence band. Fine. Okay, this is one important thing. Let me discuss this with you first. This is also one more important thing. So as a conclusion, let me discuss it with you. See, N types we had seen. So for N types, the majority charge carriers, N type, the majority charge carriers are electrons. Always remember this. We have to use this also in PN junction. Electrons are majority. Why? Because you had seen electrons were more. Pentavalent were keep on giving their atoms, right? Electrons. While in minority, we had the holes. In minority, we had the holes. But if we talk about p-type conductors, in majority, you have holes. Number of holes are more than number of electrons. While in minority, you have the electrons. This is all about p-types, n-type, extrinsic, intrinsic. One relation is there which you should remember. Ne is number density of electrons, and H is number of holes, and I is number density of intrinsic semiconductors. Fine. These are all. So when you take the relation between all these three, the relation between all these three is Ne into Nh is equal to Ni squared. All right, this is all the relation. This is just a relation between them. Just remember it, number density of intrinsic. Why we have written? Because even if you write Ne or Nh, both will be equal to each other. So it's better if we write as Ni only, representing both of it. That is written as Ni only. And Ne is for N type, N is for P type, number of holes, for intrinsic, extrinsic. So I hope I am clear to all of you. Note down all these portions. Wherever you are getting stuck, text me in the chat column, or you can unmute yourself, you can ask me.
Ma'am,
Yes, yes, Anushka, say.
ma'am, could you explain the meaning of an extrinsic semiconductors again?
Yes, yes. See, extrinsic, intrinsic have just one basic difference. In intrinsic, if we had entire, let's say, germanium crystal, you have a crystal of germanium. So all the atoms of germanium are only present. So it is pure. Only single type of element is there. But when you add it, so that type is known as intrinsic. But when you add another element, any dopant, it means any element from your periodic table. Choose any element. Let's say indium. Indium you have added in germanium. So now this is not pure germanium, germanium, germanium. In between you are seeing indium. So these semiconductors which become impure because of addition of any atom, these are known as extrinsic semiconductors. Clear?
Yes, ma'am, clear.
Now class, we have PN junction as the next topic. See, PN junction is a single crystal you have. Now, one half is doped with P-type and other half is doped with N-type. It means one half of the crystal is doped with pentavalent impurity, second half is doped with trivalent impurity. See, usually how P-type is formed in one crystal, you entirely dope it with the trivalent, then that gives you P-type. And if you completely dope it with pentavalent, that gives you N-type. But here, what are we doing? One half portion of it, we are doping it with trivalent, that is making the rise of P-type. And the other half has been doped by pentavalent, that is giving rise to N-type semiconductor. So one side you will be having holes as the majority charge carriers, and on one type you will have electrons. See here, the electron, the positive holes present over here. Here, the electrons, these are all the holes that are present. These are in majority in P-type, whereas the electrons are in majority in the N-type. Now, two processes occur. One is diffusion, one is drift. See what will happen because of the concentration gradient that is formed, higher to lower, electrons and protons, the positive holes will move. So holes will move from P-type towards an N-type and electrons will move from the N-type towards the P-type. So this movement of the majority charge carriers from N-type or P-type respectively, this is known as diffusion. This process is known as diffusion. Movement of holes from P-type towards N and movement of electrons from N towards P. This process is known as diffusion. Now see, when a positive hole will move, it will leave a negative entity over here. Negative ions will be left. And when electrons will move, positive holes will be left, right? So this positive and negative, this is arised and near a junction. This junction is the boundary of P and N type. So at the boundary of N and P type, you will see positive holes that are created and negative ions that are created. Why? Because deficiency of electrons and holes. Holes moved from P type and moved from the electrons moved from N type. So this created this layer of positive and negative ions. This layer, this thickened layer, this is known as depletion region. This layer is known as depletion region. Fine. Now what will happen? Because a potential will be set up because of the positive and negative ions. So this potential will oppose the further movement of the majority charge carriers. So in return, what will happen? The electrons from the P type and the holes from the N type will move. It means now the minority charge carriers are moving. Why? Because this electric field that is formed in response to the barrier potential, this potential will set up electric field. Electric field will allow only the minority charge carriers to move. The flow of minority charge carriers from P type or N type, this is known as drift. So this phenomena occurs. And see, when charges were moving because of diffusion, we call it as diffusion current. If charges move because of drift, we call it as drift current. So these three phenomena occur. Flow of majority charge carriers across the junction. It means flow of holes from P and N to N and electrons from N to P. Barrier potential is what? It is the accumulation of charges in P and N region that sets up a potential difference, which is known as the barrier potential. This potential difference sets up an electric field across the junction, which opposes further movement of majority charge carriers. So because of this opposition, drift develops, which means flow of minority charge carriers, which move across the junction, known as drift. So drift and diffusion and the barrier potential. Again, this is the same thing. N-type majority charge carriers are electron, minority holes, and P-type majority are holes, minority electrons. Now you have two types of, we'll study diodes. In diodes, you have two types of biasing. So note down these two portions, then I'll tell you what is biasing. Forward biasing and reverse biasing we have to do.
Ma'am, could you go up for a minute? Yes, ma'am, done.
So see, PN junction, you have understood PN junction was the same junction, but if metallic contacts are connected to make it more usable and to produce its application. So PN junction diodes are connected, but diodes are made, and these metallic contacts then get attached to the wire so that a complete circuit is formed. And whatever processes and phenomena you have studied in current electricity, same will apply. The numerical part also will be the same thing it will be. So I'll tell you that, but before that, see, drawing this entire junction every time is not possible because so many circuits are drawn. So a better way to represent it, the P part is represented by a triangle and the N part is represented by this standing straight line. So if you have to represent PN junction, you will represent it by like this. And if you have to represent NP junction, means N in front of P and ahead of P, then you will represent it by this, whatever way you have to represent it. So instead of this part is exactly representing this whole entire diode only. Now, two types of biasings are observed. These are also very, very easy part. It is just understand few points in this. First point, how to identify whether it's forward biasing or reverse biasing. See, if the P type is connected to the positive terminal of the battery and N type is connected to the negative terminal of the battery, then we call it as forward biasing. Fine. P connected to the positive part, N connected to the negative part. P to positive, N to negative. Forward biasing. Now, 4 points you have to remember under forward biasing. See, first point is that flow of majority charge carriers occur in forward biasing. It means electrons will move from the N type and holes will move from the P type. So flow of majority charge carriers occur. Then the net barrier potential, that will decrease. Barrier potential, it will decrease. The width of depletion region also decreases. The depletion region, no, that gets created in between the negative, these negative parts that are present and the positive holes which are present. This depletion region, its width also decreases. And resistance of the depletion region decreases. Therefore, current increases and we measure the current in milliamperes. An ammeter, if it is connected in the circuit, then it is measured in milliamperes. Fine, I'm repeating. In forward biasing, P type is connected to the positive terminal of the battery, N type is connected to the negative terminal of the battery. It's the flow of majority charge carriers that occur across the junction. Net barrier potential decreases, width of the depletion region decreases, and resistance decreases. So current increases, which is measured in milliampere. Now see, next you have reverse biasing. Just all the things will be opposite. See, P type is connected to the negative terminal of the battery and N type is connected to the positive terminal of the battery. This is P type connected to negative terminal of the battery and N type connected to the positive terminal of the battery. Reverse, in forward you had P connected with positive, N connected with negative. In reverse you have P connected with negative, N connected with positive. Fine. So again, same 4 points. There in forward biasing, flow of majority charge carriers occurred. In reverse biasing, flow of minority charge carriers will occur. Barrier potential decreased in forward biasing, barrier potential will increase in reverse biasing. Width of depletion region decreased in the forward biasing. Width of depletion region increases in reverse biasing. And what happens to the resistance? Resistance decreased in forward biasing, remember? So here resistance increases, whereas current decreases. So current is measured in a very less quantity, that is microamperes. This is the difference. Now in the circuits, how to identify? Do one thing, note it till here, then I'll tell you identification of reverse and forward biasing. Rest of the part is recap of current electricity. Quickly note it from here. C class, the identification. How to see whether it is in forward or reverse bias while in a circuit. Because if it is the complete circuit is given, then you'll be able to identify positive, negative. But if it is a part of the circuit, then it will be difficult for you. C class, how will you identify? If the P is connected to the higher potential and N to the lower potential, then forward. If P to lower, N to higher, then reverse. P should be connected with higher for positive. If this is not the case, reverse it. Like the first example, 10 volt is there, 3 volts are there. So 10 volts and 3 volts. P is connected to 10 and N is connected to 3 volt. So higher, lower. P connected to higher, N connected to lower. This is forward biasing. Coming to second case, P is connected to 3 volt, N is connected to minus 3 volt. 3 is higher, N is lower. P is connected to higher, N is connected to lower. So again, forward biasing. Look at the third one. This is 10 volt, this is 5 volt. This is higher, this is lower. P connected to lower, N connected to higher. Wrong. It means reverse it, so reverse biasing. Quickly answer it for the fourth part in the chat box. All of you. I should see everybody's answer for the fourth part. Forward or reverse? Just write F or R. F or R. That will be sufficient. So only one student has answered forward, everybody reversed. See, this is minus 10, this is minus 3. Minus 10 and minus 3. If you compare this, minus 3 is higher. No, this is not positive 10 or positive 3. This is lower. So P connected to lower, N connected to higher, reversed biasing, not forward. Fine. So yes, most of you were correct. All right. For the fifth part, yes, class. For the fifth part, tell me. Then sixth is exactly same. Fifth part. Forward or reverse for fifth? Okay, Ahmed answer. Yes, Ahmed, you're right. Others as well answer. Ahmed's answer is correct. Forward or reverse? Just write F or R. Rehan is also right. See class, this symbol is the symbol of earthing. Good, Fatima. Correct. See, this means 0 voltage, earthed. And 0 here, 5 here. P connected to higher. This is lower now. So it means forward biasing. So this is again, this is also 0, here minus 2. Now this becomes lower because this is less than 0. So this part, this is higher. So this will be reversed. Noted down class. This is how you identify. Done.
Yes, ma'am.
Last part for today. Almost the lesson has been completed. Just some portions are left that we'll do next Saturday only. See, in your circuit now, if you're able to identify, yes, this circuit is forward biased, it means you're able to see P connected to the positive terminal or a higher potential. Then the diode, just replace this diode by a single wire. Like we make the circuit short circuit, like that only. And if you're able to identify reverse biasing, then make it into an open circuit. Just remove the diode as if the diode wasn't there. I'll show you the example. See, this is one question. So here, this P is connected to the positive terminal, N is connected to the negative terminal. This means this is forward biased. Here, N is connected to positive while P is connected to negative. It means this is reverse bias. So what did I tell? Forward, make forward as a straight wire. Straight wire, then a resistor, 10 ohm. This as open circuit means even if the wire is there or not there, that doesn't matter. You have opened it, means no current will flow. Don't even draw it. Then the last part will be this, 10 ohm. So equivalent resistance you have to find out. You can see both these are connected in series. Equivalent resistance will be 10 plus 10, that is 20 ohms. Even if you have to find out the current will be potential divided by the resistance, equivalent resistance, which is 0.5 ampere. This is how you solve the questions for it. Note down it. Now all the questions, any type of question will come, you have to relate it with current, electricity. See, just the identification of forward, reversed. What did I do? I applied all these these were of current, electricity only. So now you have to go back to current, electricity and revised for the solving part of it. All right, note down these 2 points. Text me done, all of you when done. Then I'll stop it because now just 2 graphs I have to show you and rectifiers graph also. So half an hour topic is left that we'll cover on next Saturday only. Then your revision class will start. So revise electrostats and come, so that any particular topic also you're having any doubt in a particular topic, that can also be revised. Those who will complete, just text done, then I'll stop the class.